Welcome to the seminar series in the Gemini Center on Quantum Computing. Today we have Carlos Cid with us. He's the director of Simula UIB, and the research, which is a research center in cryptography and information theory in Bergen. He is also a professor at the Okinawa Institute of Science and Technology, where he leads the applied cryptography unit. Before joining Simula and OIST earlier this year, Carlos spent almost 18 years in the information security group at the Royal Holloway University of London. His research interests include the algebraic cryptanalysis of symmetric and asymmetric key algorithms, design and analysis of primitives for privacy-preserving cryptographic mechanisms, as well as the design and analysis of quantum-safe cryptographic constructions. So without further ado, Carlos, please take it from here.
Okay, thanks, Fran, and thanks for the invitation and for everybody for attending. And so you did the introduction, so I don't need to say much, but in the areas of interest, so we're going to focus on the last topic, which is about quantum safe constructions. So what we're going to, I'm going to do a crash course on cryptography. So I think most of you, so I'm a mathematician and a cryptographer. I'm not a physicist, but I think the background I assume from most of you will be more in physics and quantum mechanics. So just going to discuss a little bit of how we use cryptography and today, and why the developments in quantum computers and quantum information science in general affecting the research that we're doing in cryptography. So this is a definition, quite old, of a definition of cryptography, which is related to mathematical techniques, and which we can think about a tool set for addressing and providing some secure service, for example, confidentiality, data integrity, entity authentication, and data origin authentication. And now, historic cryptography has been associated with encryption, and this is one of the services mentioned above, which is confidentiality. But now has developed into a much broader area, which is the intersection of computer science, mathematics, system engineering, and it plays a key role in information theory. Now, we all use cryptography, and we use cryptography all the time to secure a couple of things that we want to do in the digital world. So the traditional one, the classic and the classical use of cryptography was to secure communications. So you had two parties that want to communicate, and then you try to use the cryptography to provide, let's say in this case, confidentiality. So we have here Caesar and one of the classic electromechanical machines. In the modern setup, we use cryptography to provide security in communications, and then this goes beyond confidentiality against, power of adversary. So the idea of the power, the capability of adversary is going to be mentioned a couple of times during the talk. So here we have, Alice and Bob. Usually we have the names, but normally the communication will be between, say, two computer systems. So in the case here, most likely laptop or the browser, and for example, in a web server. And you like to have a communication which is secure against adversary, and we have to define what the adversary can do. So this is what the power of adversaries are. And you like to kind of sort of provide almost this pipe here. Now, beyond communication, we also we use cryptography for secure storage. So cryptography for secure data at rest. So the idea here, the information is no longer ephemeral. So you may want to keep, and your adversary now is also at the endpoints, not only in transmission, but now you could think the adversaries could be either some parts that have access to the systems, or maybe, for example, hackers and so on. And maybe a more recent application of cryptography is for secure computation. So the idea here that you just don't want only to transmit data securely, to store securely, but you also want to process data securely. For example, do some statistics, share, do some collaboration, and so on. So the traditional security for this type of application is that you decrypt the data and you process it. So the issue here is that you have to extend the trust between all the parties. So you can think, for example, you have some data in the cloud, and then to process this data, maybe the cloud has a more powerful resource than you have locally, and well, you have to decrypt and give access to the cloud owner to your data. But now cryptography is being used also for some interesting applications, in which, in this case, you can do some computations and without actually having to disclose information. So here there's a picture which you can think that is performing a protocol, which is a private set intersection. So here, this is a kind of application that exists today, that you have a set of customers from B, and then, for example, you have Facebook or some Silicon Valley company, and then had the ad views, and you like to share this information to know exactly how many of the customers actually have watched the ad. And so this is part of the business model of some of the advertising companies. So this is actually being deployed every day. But in the context of security, so cryptography in the quantum world, we're actually going to go back to the first application, which is communication. So how modern secure communication works. So here, normally what we do, use cryptography. We use encryption schemes to provide confidentiality, and we use authentication schemes to provide authenticity, and we also need key establishment schemes, which is to establish the keys between the parties that want to communicate. So here, just giving a quick view of what the kind of algorithms that we use. So for message encryption, we normally use what we call symmetric encryption algorithms. So they operate over a shared secret key. So you use the same key for encryption and decryption. So I have a couple of examples here, for example, AES or string ciphers. So these are used, for example, in the communication that we have now over Zoom, or when you have a conversation over your mobile phone. These are very efficient. And the key length, which gives the security, is between 128 and 256 bits. And the security of a encryption, a symmetric encryption, is typically that there is no attack that is better than exhaustive key search. So when a designer of such an algorithm comes and makes a claim, that the best way to attack the cipher is actually by trying all the keys. So this gives a very, assume that this claim is valid, this gives a very clean way of assessing the security provided by this algorithm. For method authentications, usually you have what we call MAC, and so this is a method authentication code. So this is also symmetric key, and you have a shared secret key between the two parties. And again, it's very efficient. The key length here is usually shorter because the applications for authentication tags are usually a shorter term than actually for encryption. And the security here is forgery should be computationally infeasible. Of course, if you can recover the key, if you do exhaustive search in the key, you can, of course, do forgery, but maybe sometimes you can do forgery without actually recovering the key. Now, what is left is key established protocols. And so when you want to establish, in both type of primitives that we discussed in the previous slides, we need keys to be shared. And then key established protocols is essentially for that, is a protocol, cryptographic protocol, which allows you to share keys to be used for encryption and authentication. In some cases, you can just use what we call out-of-band key establishment. For example, it could be sent by post, or could be shared by another out-of-band channel. So, for example, if you have a mobile phone, and the key, in the sense of which allows you to do the key establishment, is shared between your SIM card and then your provider. So in this case, actually, the establishment has been done sort of out of band in a way, based on by receiving the SIM and putting your card. But more frequently, in particular the internet, you use in-band public key cryptography. So essentially, public key cryptography is used to allow to solve, originally, the original goal is to solve the key distribution problem in symmetric key. So you want to encrypt messages use a symmetric key, but before that, you need to share keys. And public key cryptography it can be seen as a tool to do this. In public key cryptography, operates under a public and a private key. And unlike symmetric cryptography, public key cryptography is mathematical by design, because you want to build what we call a trapdoor, which allows you to have this public and private key. And typically then is based on some hard problems, mathematical hard problems, normally from algebra and traditionally from algebra and number theory. And so here you have, the most popular cryptographic algorithm, public key cryptographic algorithm. For example, the RSA public key, which is based a very simple design, is explained there. And the idea here is that the encryption is based on an exponentiation, and so it's modular a product of two large primes, which are secrets, and then you derive your key and your secret key and the private key and the public key, and they're essentially the exponents. So the security here is based on the integer factorization problem. If you actually can factor the modules, this capital N there in P and Q, then you can break this algorithm. But you may be able to recover the message without actually doing the integer factorization problem. But it's kind of believed that this is kind of the best way to do it, and then this is used the difficulty for factorization to derive, for example, the size of the keys. And here you also have what's called the Diffie-Hellman key established. So this is based on another problem, which is discrete log problem. And this is also a very simple protocol. So this is not used for encryption, but rather to establish keys. And so you have essentially you have a base, which is G, and then you have a exponent, a secret exponent A and B, and then you exchange there, and then you do exponentiation using your secret one, and you kind of reach the same secret, which is GAB. And so this is called this, if you actually can solve the discrete logarithm problem, which is essentially the logarithm, but rather than being over the real numbers, is over a sort of discrete algebraic structure, for example, a ring or a group, and then of course you can recover the A and B. But if you're not, maybe there is some other ways you can do this. So this is kind of the two most popular, at least the problems. And so just one remark. So you also have elliptic curve instance of this the Diffie-Hellman key establishment. Here is used on this group over the prime field. But you can also use an elliptic curve, which is kind of more efficient. We're not going to discuss why. And you also, in public key, you can also use you can define signature algorithms, which are defined based on the same hard problems. Okay, so how do we consider the public key cryptography security? And here you have encryption is with a public key, decryption with the corresponding private key. Signature is the inverse. You sign with the private key and verify with the corresponding public key. The performance of public key cryptography is much slower, it's much worse than symmetric key, because you do mathematical operations. And also the key length. So if you remember when I talked about symmetric key encryption, I said between 128 bits and 256. And the key length for public key cryptography is much larger. And the reason is because there are some shortcuts. You don't try every key, you don't do exhaustive key search, but rather you try to solve the mathematical problem. So actually deriving the key length for public key cryptography is a challenging task, because you have to think about the algorithms that you use to solve the particular problem, for example, integer factorization, and then kind of translate this into a measure of operations. And then this gives you kind of the equivalent in, for example, of security of the AES with 128 bits. And this is kind of not very easy to do, although in the case of RSA and discrete log, there's a good understanding. But for the algorithm that we're going to mention in a minute, this is actually less the case. So the security here, as I mentioned, is that the attack is not about trying every key, but rather looking at some dedicated algorithms to solve the underpinning mathematical problem. So based on this very quick and crash course. So this is actually how modern secure communication works. So for example, here is this very simplified version of TLS, which is the protocol used in the internet. For example, your browser when accessing the Amazon website. So the client, in this case, will be your browser, connects to the server, the web server. So the client and server, they use public key cryptography to establish a shared secret. And the server use digital signatures to authenticate itself to the client. So in this case, normally only the server, but you could actually have protocols in which both parties need to authenticate. And then after they share this key, they use this secret. They use this to derive keys for encryption and authentication, which we kind of mentioned before, and then in symmetric key, and then they use actually that to encrypt and authenticate messages. So in practice, in the real world, public key cryptography encryption is not used to encrypt messages, but rather encrypt or at least establish keys, share secrets, which then is used to derive the keys that you're going to actually do the encryption itself, and then you use symmetric key cryptography. So, for example, in this sort of protocol here, imagine if you want to aim for 128-bit security. In this case, the symmetric algorithms, you should use 128-bit keys because that's the way the security is derived. But for public key is kind of a little bit tricky. So in this case, if you're using RSA, your model should have about 3,000 bits. And the same thing if you're using discrete log based, and your prime has 3,000 bits. But if you're using elliptic curves, you can actually have 256 bits. And that's the reason here there are some attacks that work on the mod P that don't apply from elliptic curve. Okay, so that's kind of what we have in cryptography. So now let's move to the quantum world. So we go from classical to the quantum security. So the first question here is, what do you mean for an algorithm to be considered secure? And so when you design an algorithm, you kind of have to define how it's used, the environments, and the adversary capabilities. So for example, how the adversary can interact with the algorithm and the computer capabilities, how much data is available, how much memory is available. So in the quantum world, the first change that we have is that we allow the adversary to have a quantum computer, so a scalable and fault-tolerant quantum computer, to perform computations in the attack. So this is the first step that we give. Essentially, we give the adversaries now a quantum computer. So of course, when you think about this, the first question is, well, can we just then run the attacks much faster than we had? And of course, that's not the case. In quantum computers, you just don't run your classical algorithm against for example, to break your ciphers, but rather you need dedicated quantum algorithm that can explore the architecture of quantum computers and for the application that you want. In the case of cryptography, for symmetric key, the algorithm that we can consider is Grover's algorithm, which allows you to do a key exhaustive search rather than 2K operations on the square root. So in kind of the effect here that you could think that the security of AES with 128-bit keys fall from 120 bits to 64 bits. So one remark here that this is not that simple because the complexity of Grover's is asymptotic, so there is some overheads, and the overheads, there's been some research showing that this is actually quite very high. So you don't translate exactly from 264 asymptotic to 264 AES encryption, which would be equivalent to 64 bits of security. So that's a kind of much higher. So I think it's the estimate is now something about 90. But even though in this case, you can always just switch from AES 128 bits to 156. This doesn't cause much problem in performance. So AES 256 is in theory just 40% slower because there's a few more rounds from 10 to 14. And so this is not really anything of concern. On the other hand, for public key cryptography, this is a completely different game. Shor's algorithm breaks RSA, elliptic cryptography, and DSA, Diffie-Hellman, and so on. So then this is a polynomial complex algorithm, so it essentially gives exponentially faster than best class. So the consequence here is the public key cryptography. I mean, the standard that we have to use today is no longer secure when the adversary can have access to a large enough quantum computers. Now, the question is this really a threat? Of course, I think we all know that building quantum computers is a very challenging task. But there's been a lot of investment and progress in the past couple of years. So this is actually just for last month. IBM showed information about a new quantum computer, but there's also some optimizations, the algorithmic aspect. So, for example, here is showing a paper from 2019 showing how to factor a 2048-bit RSA modules in 8 hours using 20 million noisy qubits and so on. Now, we can always argue how far we are from quantum computers, but this is actually the progress, and the expectation of progress actually has caused already a lot of concern. So recall the way communication normally work is based on a public key exchange and then symmetric key, bulk encryption. And so this gives rise to what we call today collect now the Cryptulator attack model. So in this case, what you could happen is the adversary could be collecting this key exchange and then the encryption and just storing there. And then maybe in 30 years, when they have access to a large enough quantum computer, they can go and then they can recover the shared secret that was used and then derive the keys, the symmetric keys that were used to encrypt the message and then decrypt. So this is kind of relevant, particularly for information which has a long-term value, for example, government information or medical data and so on. So this has led to a lot of effort in designing and analyzing and standardizing what we call quantum safe algorithms, PQC, and also a lot of industry support for transition and also quantum risk management. So this is in the last two items is very active in industry and how to do the transition and also how to manage the risk that presented by implementations today. So this leads to post-quantum cryptography, which is the first item. And so post-quantum cryptography is no algorithm that run in quantum computers, but rather they are classical mathematical post-quantum public key schemes for which there are no quantum algorithms that can provide exponential speed up, as is the case of the short. So this is normally people call post-quantum cryptography, but now it's being rebranded as quantum resistant cryptography, which I think is a better name than post-quantum cryptography. That causes a lot of confusion. Now, mathematics is, you have a lot of hard problems in mathematics. So can you just build one if you mathematician and you work on something that has some kind of difficult problem? Can you just build a crypto system around it? So this is actually this is quite difficult. It's not non-trivial because you need to define this trapdoor, and then achieving security, is also quite hard. So there's several different proposals for underlying mathematical problems for post-quantum cryptography. For example, solving hard lattice computational problems, decoding random linear codes, solving systems of multivariate quadratic equations, recover exogenous mapping between elliptic curves, and so on. So here, I'm just going to, we're kind of running a little bit out of time, as usual, a little bit behind. So Franz, how much flexibility I have going beyond 30 minutes?
I think it's if you go a couple of minutes over, there's no problem. Just
okay.
Go ahead.
So I'll try to speed up a little bit now. And so here I'm just going to give a quick overview of, without going into detail, of the ones based on the first two problems, solving lattice problems and decoding linear codes. So the first family of post-quantum cryptography schemes is called lattice-based cryptography. And the idea here, the difficulty is related to solving, the security is related to solving some hard problems in lattice. For example, the short vector problem. So in this picture here, you can see that you have a lattice and you have a basis in black with U1, V2, and also you have another base in U1 and U2. Now, U1 and U2 is a better base for a lot of problems you want, but V1, V2 is also a valid one. And you might be looking for the smallest vector, which will be U1 or minus U1. And it's not trivial to, well, in 2 dimension is trivial, but it's not, normally in high dimensions, it's not easy to find the short vector, for example, U1, if I'm giving V1 and V2. In practice, the schemes are not described as lattice, but rather most of them are based on a problem called learning with errors. And so the idea here, the learning with errors, is that you can think that you have a linear system, which your secret is S1, S2 to Sn. And then you multiply this by a matrix, so it gives a linear system. So if you, it's quite simple to solve, but if you add some errors, which is this vector E1 to EM, and this is quite difficult it's very difficult to recover S1, Sn. And of course, there's a lot of assumption here, for example, on the distribution of the secret, distribution of the errors, and so on. So the LWE-based schemes, they're quite versatile. They use for both encryption, and normally we call key establishment mechanism because we don't use it for encryption per se, but to establish key, and also for signatures and much more. And they have a good profile. The concrete security, so the size of parameters, remain an area of research. And lattice-based is becoming the de facto standard for post-quantum cryptography and security. And we're going to see why in a minute. Code-based cryptography, the security is based on schemes, the difficulty of decoding random linear codes. So this is an idea that goes back more than 40 years, proposed by McLeese, and it's based on Goba codes. And the details here we can skip, but essentially what you have a code, which is a linear code, which is decoding is efficient, but then you kind of hide this code in some way by doing some permuting the columns and doing some other operation. And then this is your public key, and then now it looks like a random linear code. And so the encryption, you encrypt a message by adding some errors. And the decryption, and this is the public key, and then the decryption, because you have the original code and you have the matches they use to obfuscate the original one, you can recover the original one and then do the efficient decoding. And the security of code-based cryptography is very well understood. It's quite good for encryption, but not so much for signature. It's fast encryption, efficient decryption, and the ciphertext is quite small, which is good, but it has a very large public key. So public key is for some levels of security is about 1 megabyte. And so this is actually code base is considered more like a conservative post-quantum cryptography choice. So it's not suitable for all applications, but there's some applications which are considered suitable. And this leads us to the NIST post-quantum standardization process, which is the US National Institute of Standard Technology. And then they announced a competition in 2016, and then it's been running for a large number of submissions, and leading to the third round in the summer 2020. And then here gives a little bit of what type of algorithm they consider. So you can see for encryption, they had 3 lattice-based and 1 code-based. And for signature, they had 2 lattice-based and 1 multivariate. But they also kept some other schemes because they consider promising. For example, if there was some cryptanalysis or so on. So here is the selection. You can see in the signatures, you had 2 lattice and rainbow. This is after several years of analysis. But in February 2022, there was a paper showing actually how you can break rainbow taking a weekend in a laptop. So remember, this is a proposal that was close to standardization for quantum safe. So essentially, the quantum computers could not. And by here showing how you can use just your laptop today to break in 53 hours. In July this year, there was selected the algorithm. So actually in public key encryption, there's only one that was selected, Kyber. And then for digital signature, of course, Rainbow was not selected, but they selected the two, Latticebased and another one called hash-based, which is the Sphinx. But they also announced a few more for encryption that be considered for a fourth round. So for encryption, they only select one based on lattice. So be wise maybe to select another one for standardization, which is not based on the same problem. So this is quite common in cryptography that you try to balance and have different options that they know. So here you have three, which are code-based, and you have one which was isogenous based. So in the one classic Machiavellis, I'm part of the submission team based on we merged to one of our submissions, which was NTS Chem. So this was in July 2022, showing this 4 candidates for the fourth rounds. And then a few weeks later, there was a paper showing an attack against the isogenous-based one, which essentially completely broke them. So this is I have this just illustration that this area is not very mature, even after several years of a lot of effort. And when we're getting closer to standardization, a paper will come out and not breaking only theoretical, but actually breaking practice. In some cases, over the weekend in a laptop. In this case, here is the same. So just final thoughts here. And so this is also, there is a new call for signatures because of the choice that is still lattice-based. There are several risk uncertainties related to the size of the parameters, so the parameters of these algorithms. So remember, public key is based typically on the best mathematical algorithm, dedicates mathematical algorithm to break the underlying problem. And this is, keeps evolving, and this means that the security, your parameters might have to grow to provide the security that you claim. There's a lot of calls for hybrid deployment for the next years. And there's expectation that a code-based non-lattice will be selected as well as part of the fourth round. And there'll be a lot of work on transition in the coming years. And beside that, there's this is not the only work on Postquantum. Besides encryption and signature, there's also other primitives that you like to have Postquantum version. For example, oblivious pseudorandom function. There's for zero knowledge proof systems. So there's a lot of work also. They typically base a lot of these constructs are based on elliptic curves, and you like to have versions which are, say, based on some lattice basically. So I'm just going to close in the next 2 minutes. So this will be very quickly. So this is beyond post-quantum cryptography. So one thing which, of course, I didn't mention is quantum key distribution. So quantum key distribution, solves the same problem of post-quantum key establishment mechanism. And in this case, now you can consider as an out-of-band protocol, which use a quantum communication channel. One thing it also requires a classical authentic channel, and the claim here is they offer information theoretical security against eavesdroppers. So there are two protocols which are kind of well known, and BB84, which works by encoding the bits that the qubits that you want to send based on different bases, orthogonal bases, and then this is actually the measurement by the other party, and will give you the agreement, and then also the detection against eavesdroppers. And you have also a version which is by Eckert 91, which uses entangled qubits, and the agreement now is based on the Bell inequality. So there are several real-world deployments, but the benefits of compensated post-quantum cryptography is subject to debate, which we don't have time to go through. And then beyond that, and this I'm just going to finish, you can go look at some other work on cryptography in the quantum worlds. And in this case is that you can think about extending a bit more the adversarial capabilities. So for example, here I'm using a terminology from Magnai Placentia, which is she called Q0 is the classical word in which you have the adversary has class computation and classical data queries. The post-quantum world is that you have also a quantum computation. The adversary has a computer, and then what's it called Q2, which we don't have a name for that. Maybe sometimes could be called post-quantum. In this case, besides a quantum computer, you can also, the adversary can do quantum queries. So essentially, your algorithm is implemented in a quantum computer as well. So that now you can query your algorithm using superposition. And it does happen, and without going into detail, that in this case, some symmetric key constructions, they can be broken quite trivially if you allow the adversary to do quantum queries. So I have a construction here, which is called the Even-Mansell cipher, which is a very simple and the classic secure is very well understood and is exponential. But if you allow quantum queries, you can use Simon algorithm to break this trivially. So to close, research in this area, there is some research interest in looking at what we just discussed a minute ago, which is a quantum cryptanalysis of symmetric primitives. So it should be quantum cryptanalysis, not cryptography. And there's also work on, for example, in secure multi-party computation, delegate quantum computation, and so on. And security of quantum internet is the model that you're going to have quantum internet, so requires security and cryptography will be important here. And in the real world is migration. So there's will be a lot of work in the next several years migrating, regardless whether we believe that quantum computers become reality or not. Post-quantum cryptography is becoming standard, and banks, government, and companies, they're going to have to migrate, and this is going to be a lot of work in the coming years. Sorry if I have to rush in the end, but thanks, and if you have any questions, happy to answer.
So first of all, thank you very much for this very interesting talk. Very good. Are there any questions from the audience?
Yeah, I have maybe a question. So yeah, very nice talk. So
thank you.
So like regarding AES and Grover's search. So I heard like a similar talk by Dan Bernstein and Tanya Lange several years ago, and then they also said that like for AES and these symmetric key schemes, like you only expect this quadratic speedup from Grover. Is there evidence that you cannot like? I come from quantum information theory. I don't know these protocols, but is there any evidence that you cannot like make up a better quantum algorithm exploiting some feature of AES?
Okay, all right. So that's a good question. So, and the Grover one is in a way you could argue that is slightly kind of lazy in the sense that you're just doing an unstructured search, and then you can do this in a black box. So this slide that I jumped very quickly here. So this is an example. Of course, when we think about Grover, we think about Grover in the left, attacking the AES as a box, a black box, which you have the key, and then you have an encryption of X given Y, and you like to recover the key, and then you run Grovers here. But in reality, AES is something more like the right-hand picture, which is much more complicated. So there's quite a bit of work now, and consider, for example, when you're doing cryptanalysis, because symmetric cryptanalysis is well developed, so there's a lot of interesting techniques that attack not the black box, but attack the right-hand operations, and because it's repeating rounds and so on. So there's some work, for example, at this stage, some work, for example, doing some quantum subroutines. So, for example, you might be looking for some collision. There's a lot of attacks that search for collisions. So, for example, you could use Grover as a part of a subroutine, or something a bit more clever. So there's been some work in this area, not necessarily against the AES, but for example, there's I think some work on collisions for SHA-256, which kind of has been improved. So this is actually applying more in sort of what we're doing in classical symmetric cryptanalysis using some quantum algorithms. So to answer your question, so the Grover one is the best that you can do, and is known to be optimal if you consider your AES as being the left hand here which is just a black box. But if you actually consider the structure, even though it's not mathematical, well, AES does have mathematics, but even though it's not mathematical like RSA, you could potentially be able to explore some of the structure there. So this is an area of research.
Thank you.
Okay, thank you very much. Are there more questions? If not, then thank you very much.
Okay, thank you.